So in this video lecture, we will start with the stiffness method. In this module, we will be learning about the stiffness method, the development of the stiffness matrices by the physical approach, stiffness matrices for truss and the frame elements, displacement transformation matrix, analysis of simple structures, plain truss and plain frame, nodal loads and the element loads, lack of heat and temperature effect. We will just have a quick look on the fundamentals of the stiffness method. So we know the difference between the flexibility method and the stiffness method is that the flexibility method, here the forces are the unknowns. That's why we are applying a unit force and we are measuring the corresponding displacements which are known to you. Right. In the case of stiffness method, you are aware of the forces, but here the displacement components are the primary unknowns. Number of unknowns is equal to the kinematic indeterminacy. The redundancies are the joint displacement which are automatically specified, and the choice of redundancy is unique. It is good for the computer programming than the flexibility method. That's why we are using this same principle for the STAR software. So the kinematic indeterminacy can happen at joints where the members meet. It can be at the supports and also at the free end, and also where the joints that undergo translations and the rotations. In some cases, rarely the displacements will be known to you from the restraint condition, that like the hinge is there, then means total displacement is equal to 0. The unknown joint displacements are the kinematically indeterminate quantities. So please note that unknown displacements are the kinematically indeterminate quantities. The degree of kinematic indeterminacy is the number of degrees of freedom. Then some conditions, some notes in a truss, the joint rotation is not regarded as the degree of freedom. The joint rotations do not have any physical significance as they have no effect on the members in the truss, because we are only concentrating on the axial movement, axial force in the truss, and so there is no significance for the joint rotation. In a frame, degrees of freedom due to the axial deformations can also be neglected as the values are very small and has got negligible effect on the frame members. Okay, this is a quick comparison between the flexibility method and the stiffness method. Here you are supposed to write the stiffness and the flexibility coefficient of the beam. So I'm again repeating, to find the flexibility coefficient, apply unit loads at the corresponding action points. So first you apply unit load at A1 point and get the corresponding deformations at point location 1 and 2. Then you apply the unit load at the point 2 and also write the corresponding deformations at 1 and 2. In the stiffness method, you are supposed to give the displacement keeping the other displacement to be 0. That means for the A1 there will be a vertical deflection, so the rotation should be restrained so that it will be a sinking support case. And for second case there should be rotation, but the movement is vertical movement is restricted. It will be like this, so the rotation is allowed keeping 0 vertical deflection. So the corresponding F11, F21, F12 and F22 are written for the flexibility coefficient by applying the unit force at the point 1 and 2 separately, and the stiffness coefficients are done for the case 1 and case 2 by giving the unit displacement as well as the unit rotation for the separate case and getting the stiffness coefficient. The action displacement equations for a beam subjected to several loads. So here there is a beam, continuous beam with A1, A2, A3 as a loading. So this we have previously discussed this case, so that the deflection will be like this: D1, this being this upward, there will be upward deflection, D3 due to the rotation, A3. Okay, so A1, the action 1 will be is equal to A11 plus A12 plus A13. I'm again repeating, A1 is equal to A1. 1 means the action at the 1 due to the force at the first point. Action at 1 due to the force at the second point. Action 1 force at the action at the first point due to the force at the third point. So we know that A is equal to S into D, where D is the deformation, S is the stiffness, and A is the action. Okay, so combining, A1 is equal to A11 is equal to S11 D1, A12 is equal to S12 D2 plus A13 is equal to S13 D3. Similarly for A2 and A3. Okay. So this is how you write the stiffness coefficient. So for the first case, you should note that the displacement is equal to 1 should be applied, provided the other deformation equal to 0. That's why we are providing a hinge here, so that there is no vertical displacement, and also a fixed here, there is no rotation. For second case, D2 should be equal to 1, D1 should be 0. That's why you are applying a hinge here, and this value should be 1, and this also should be 0. For the third case, you are applying a unit rotation only, provided this D2 and D1 equal to 0. So hinge at here and here, and there is a rotation. So the stiffness matrix A1 is equal to S11 D1 plus S12 D2 plus S13 D3 up to S1 and Dn. And similarly for the n actions, you have the total matrix. So the in matrix form, you can write like this, and A is equal to S into D, where A is the action matrix, stiffness matrix, and the displacement matrix, AST respectively. And you also know that F is equal to flexibility matrix is the inverse of the stiffness matrix. Okay, we will analyze one more problem. This is a stiffness method basic concept. The property cantilever is kinematically indeterminate to first degree. That is, the unknown displacement will be the here displacement will be 0. It will be pen like this, and the unknown displacement will be theta b here, which is the degree of freedom. So the degree of freedom is 1, and we are supposed to get the value of theta b. So the kinematically determined structure is obtained by restraining all the displacement, that is, all displacement components made 0 for the restrained structure. So for that, we are restraining the right support with 0 rotation. So we want to make this one also to be fixed. Hence, this is the case, and the MB is equal to minus WL square by 12. So this was the moment if there was 0 rotation at the point B. Okay, that is a taken. But the actual rotation at B is theta B. Actual rotation is theta B, and if it was fixed, it will be 0, and the corresponding moment will be WL square by 12. Then we are going to apply an unit rotation corresponding to theta B. This is actually the stiffness method. Let the moment required for this B unit rotation be MB. So this unit rotation will be theta B for and the moment required for this unit rotation is mb. Okay, we know that mb is equal to 4a by l clockwise direction, anti-clockwise direction. And for the equilibrium condition, the total moment should be equal to 0, because in real case is actually hinge. So the mb plus mb small mb theta be equal to 0 as a joint equilibrium condition, and substituting the values, we get the theta b is equal to WLQ by 48 EA, which was the unknown displacement, which is solved by the stiffness method, and the mb is the moment required for unit rotation, is the stiffness coefficient here. Okay, yeah. Then the next one is the stiffness of the prismatic members. So this will be a long session, the second half of this PPT or this video, which is similar to the last video of the flexibility method. The stiffness coefficients of a structure are calculated from the contribution of the individual members. So we are going to frame the relation between the member and the structure. Hence, the member stiffnesses are to be developed first. So these are the different cases for the member stiffnesses. So the member stiffness matrix for prismatic beam member with rotation at the ends as a single degree of freedom. Okay, as a degree of freedom. So consider a case of a fixed beam, and for providing or for obtaining a unit deformation or rotation at the point, say let be A and B. For A, you need actually 4A by L, which is the moment required, and the half will be a carryover to the right side, which is 2A by L. And similarly, applying for the B point, that is keeping this value 0 and applying unit rotation here, 4A by L will be the moment required at that point, and the 2A by L will be the carryover moment. So the stiffness matrix will be 2A by L into 2, 1, 2. Okay, based on S11, S12, S21 and S22. And if you remember the corresponding flexibility matrix for this double fixed beam, from that one it was actually L by 6 CA into 2 minus 1 minus 1 2. Taking the inverse of flexibility matrix will give you the stiffness matrix which we have obtained, which is the proof of the same. The next one will be the member stiffness matrix for prismatic beam member with deflection. Member stiffness matrix for prismatic beam member with deflection and rotation at 1 and as degrees of freedom. So for this example, you have 1 degree, 1 and 2. So for this one, you should apply the first vertical movement, that is actually it will be a single support case. So for the first case it will be like this, but this should be like this, and this delta will be equal to 1. This displacement is still be equal to 1, and for the second case it will be like this. Due to this moment, the rotation value will be 1. Okay, so this we have done previously, and the corresponding stiffness coefficient is equal to LA by L cube minus 6A by L square minus 6A by L square and 4A by L, which was for the sinking support case. And here also the verification is done that the stiffness matrix is the inverse of the flexibility matrix. Example 2, find the member stiffness matrix of the beam shown in figure with reference to the coordinate shown. So, compared to the previous one, the one was upward, two was anti-clockwise. Here, the one is downward and the moment is also clockwise. So, yeah, this was I was explaining for the previous case for this one like this. Yeah. So you should apply like this. Only thing is that there will be change of sign, and the matrix will also uh, have a change accordingly to that one. So this was the matrix stiffness matrix component 12VA cube, which is the support reaction for the sinking settlement of 1, and the corresponding moment will be 6 square. And for the case of applying a unit rotation, the 4 will be the stiffness, sorry, the moment required, and the corresponding reaction will be 6 square, which is written as the matrix. Then the next example, here the difference is only with respect to the coordinate. That is, yeah. For the previous question, the one was a vertical force and two was a moment. But here the option is one is a rotation and the second one taken as a second coordinate. So only the stiffness matrix element will get interchanged according to this one. So the first case will be the unit rotation and the second case will be the support settlement. Same matrix values 4A/L, 6A/L square, 12A/L cube and 6A/L square. It has to be properly placed in the stiffness matrix. Then some more additional member stiffness cases. So for the truss member, we know SMI is equal to EA/L, S is equal to 1 by F. Okay, so previously we have derived that flexibility F is equal to L by EA. So 1 by L by EA will be EA/L for the case of stiffness matrix for the truss member, which is actually elongating axially. Similarly, for the plane frame member, this is a plane frame member which is having axial deformation, which is having a vertical deformation as well as moment, like rotation within the plane. You are supposed to give the rotations and displacement unit value. For case 1, it was the linear displacement. Case 2 is on the vertical deflection is equal to 1. Third case is unit rotation, and corresponding stiffness matrix elements are like this: EA/L 0 0 0 12A/L cube. So this will be the sub matrix which correspond to support settlement and the rotations which we have discussed previously. Yeah, so this one. Okay, so only the EAL term will be coming into picture when it deals with the plane frame member. For the grid member, you have linear deformation, vertical deformation, and also the torsion. So it is also similar to the previous ones. So first one is the applying unit displacement along the x direction. Second is applying unit deformation upwards. Third one is applying unit rotation, and write the corresponding stiffness matrix elements. previously discussed this one, that the flexibility coefficient was actually TL by Gj, but torque when it was applied unit, then the correspondingly flexibility coefficient was L by Gj. Now the stiffness is actually 1 by F will be Gj by L. Telling this compared with the flexibility method, the last video, how we formatted for the plain grid member. For the space frame member, the member is having 6 deformation, all the axial deformation, all the coordinate deformation, as well as the torsion, as well as the moments in various direction. So there will be 6 by 6 matrix, because 6 unknowns are there. There will be 6 by 6 will be the matrix size. Next is the formalization of the stiffness method. Explanation using the principle of complementary virtual work. This will be a detailed one. Yeah. So we know AMI is equal to SMI into DMI, where A is the action and D is the displacement, S is the stiffness matrix. DMI, it contains the related displacement of the K end with respect to J end of the ith member. If there are M members in a structure, there will be M action matrix, and also SMM will be the stiffness matrix size, and the DM1, DM2 are the individual member displacements. So we have for an individual member, AM is equal to, which M stands for the member, AM is equal to SM into DM. In the matrix form, AM is equal to SM into DM. SM is the unassembled stiffness matrix for the entire structure. So this is called so because we are actually writing the stiffness matrix for an individual member. We want to club it in the proper order to make the stiffness matrix for the entire structure. So currently it is an unassembled stiffness matrix. Then some more definitions, that is a relative end displacement in DM will be related to the vector of joint displacement for the all structure ds by CMS. It is a displacement transformation matrix. For the flexibility method, we learned the load transformation matrix, right? So CMS is the displacement transformation matrix. This is the compatibility matrix, and the DS, it consists of free unknown joint displacement and the restraint displacement. In the previous, for the flexibility method, it was a joint load and the restrained reactions. Okay, DJ and DR. Here. For the flexibility method, it was AJ and AQ. If there are no support displacement specified, then DR will be a null matrix. It is actually the restraint displacement, right? So the DR will be a null matrix. So DM in a expanded way, DM is equal to CMS into DS. Our equation is equal to CMJ into CMR. Will be the joint and the restrained transformations into DJ and DR, which are the free joint displacement and the restraint displacements. Now, next title is the elements in displacement transformation matrix. So, we are going to focus on these elements in this matrix. Compatibility matrix. CMS are found by the compatibility condition. CMJ and CMR. CMJ and CMR are the displacement. It is the joint displacement transformation matrix and the restraint displacement transformation matrix. Relate to the DM to dj and dr respectively, which is actually discussed in the previous equation. So each column in the submatrix of CMJ consists of the member displacement caused by the unit value of the unknown displacement applied to the restraint structure, and CMR consists of member displacement caused by the unit value of the support displacement applied to the restraint structure. So there is a difference between the CMJ and CMR. CMJ is the member displacement caused by the unit value of unknown displacement applied in the restraint structure, and CMR is the member displacement caused by the unit value of the support displacement. Suppose an arbitrary set of virtual displacement is we are applying some delta dm is applied to structure. This delta dm is applied to structure because this is actually the member displacement. The external virtual work produced by the virtual displacement delta ds and the real load as is delta w is equal to as transpose into delta ds. So AS is equal to, we know, AJ into AR, joint and restraint actions respectively. DS will be DJ and DR. The internal work produced by the virtual relative end displacement delta DM and the actual member action AM is similar to the delta W. Delta U is equal to AM transpose into delta dm for the member case. Equating the above to the principle of virtual work, AS transpose into delta ds is equal to AM transpose into delta dm. We know that dm is equal to CMS into ds, CMS into ds, and delta dm is equal to CMS delta ds. Delta dm is equal to CMS into delta ds. Also, AM is equal to SM into DM. AM is equal to SM into DM. So the known equations. Hence, AS transpose into delta DS is equal to, we have AM transpose. So this SM transpose into DM transpose will comes into play. And DM is equal to CMS into DS. So clubbing all those things, AS is equal to CMS transpose into SM into CMS into DS. So AS is equal to SS into DS. AS is equal to SS into DS is the obtained equation where SS is equal to CMS transpose into SM into CMS. Is the assembled stiffness matrix for the entire structure. Then it is useful to partition the SS into submatrices pertaining to free unknown joint displacement dj and restrained displacement dr. The AS is equal to SS into DS. This one equation is equal to AS comprised of joined actions and the restrained actions is equal to SJJ, SJR, SRJ, SRR into DJ, DR, where SJ is equal to CMJ transpose into SM into CMJ and SJR is equal to CMJ transpose into SM into CMR and SRJ is equal to CMR transpose into SM into CMJ and SRR is equal to CMR transpose SM into CMR. Hence, we'll get applying these values A, J, and AR. As this equation from the matrix, and the first one implies that DJ is equal to, on rearranging, SJJ inverse into AJ minus SJR into DR, which is the joint displacement. If there is any support reaction, that is, if actual or equivalent joint loads are applied directly to support, then one more term will be required to be placed in this equation. AR is equal to minus ARC plus SRJ plus DJ, SRJ into DJ plus SRR into DR, where ARC represents the combined joint load. It is actual and equivalent applied directly to the supports. The member end actions AM is equal to SM into DM is equal to DM can be written as CMS into DS by the displacement transformation matrix. The final values of member end actions are obtained adding member end actions calculated as above and the initial fixed end actions. So AM final is equal to AMF plus SM into CMS into DS, where the AMF, it represents the fixed end actions. So these are the derived formulas. The joint displacement dj is equal to this equation, and the support reaction AR is equal to, and the member end action by the last equation. few more slides. The relationship between the force transformation matrix and the displacement transformation matrix. So this one we discussed for the flexibility method, and this is the subcomponent of the stiffness method. So we know delta AS transpose into DS is equal to delta AM transpose into DM. These are the corresponding values. AM is equal to BMS into AS. Delta AM is equal to BMS into AS, which are the force transformation matrix. Delta AMT is equal to delta AS transpose into BMS transpose. Similarly, we know DM is equal to CMS into DS, which relates the member displacement matrix with the structure displacement CMS. So delta AS transpose into DS is equal to delta AM transpose we have derived like this, which relates the load transformation matrix. Delta AS transpose into BMS transpose into DM we have is equal to CMS into DS. Hence, on cancelling values each other, DS is also getting cancelled. So the BMS, this is actually 1, left side will be 1. BMS BMS transpose into CMS will be an identity matrix. This is the relation between the force transformation matrix and the displacement transformation matrix. Problems we'll discuss in the next slide.